welcome to our talk. There were indeed some major news scoring the headlines about last year about some Java deserialization vulnerability affecting many products, open source and commercial products, being remotely exploitable, leading to remote code execution, affecting thousands of potential installations, and even some vendors have been affected. So this was something where some mitigation advice was also making the rounds. And in this talk, we're about to discuss a little bit of the differences between these different mitigation advices, whether they do work or whether they do not work, whether they can be bypassed, and we'll show you some bypass techniques also, and we'll give you tips how you can spot these kinds of vulnerabilities in static code reviews and also doing pen tests. So just a quick poll. Please raise your hand if you're somewhat familiar with what this code is doing. Okay, that's good. It's actually deserializing something untrusted from an outside source. And how many of you are familiar with the inner workings of the read object method? So what's basically the JVM is doing under the hood when deserializing something? Oh, okay, a little bit less. And finally, this can lead to a remote code execution. So that's basically some exploitable code that attackers can exploit to gain a remote code execution on a system. And we will cover this in detail in this talk as well. First, just a quick recap of what Java serialization is about. It's, roughly speaking, a way to exchange data between two different entities, two different Java systems, usually remotely. And these kinds of data is just some object graph that's being serialized to a byte array or byte stream representation and then deserialized on the receiving end and reconstructed. Obviously, only data gets serialized, not any code, obviously. So the code sits on both parts, the receiving end and the sending end, and sitting there on the class path in terms of being the same class. And even though you might now think that you're not really directly affected by this vulnerability because you're not using any kind of serialization technologies within your own applications, it might be that you're still at risk because there are many frameworks and technologies, just a few of these on the slide, like RMI, JMS, JMX, and HTTP invokers, etc., that are heavily using Java serialization under the hood. So you might eventually, without knowing, exposing deserialization interfaces within your system architecture.
So in order to understand how these attacks work, it's crucial to understand what is going on behind the scenes when we call a read object on the object input stream, the quick poll question that Christian was doing before. So basically, what we will be doing from our code, from the application code, we will be reading some bytes from an untrusted source, maybe a request, maybe a socket connection, maybe a file that can be controlled by the attacker. And we will be basically wrapping those bytes around an object input stream, and we will be reading objects out of these bytes. So when we call the read object method, we will be basically dispatching the execution to the object input stream that will basically extract the class names of the objects that are about to be deserialized from the byte stream, and basically we'll start loading those classes from the local class loader and looking or expecting these classes. So if in any of these classes they find a deserialization callback, like for example the read object or read resolve, object input stream will invoke these methods in order to customize the deserialization of these objects. So that's something that developers use to customize the way or the data that is deserialized during this process. So after the object has been completely deserialized, the object is returned to the application code. Well, it will be cast into the expected type. So if everything goes well, there will be no exception here. The code will use the object as expected. And then at some point, the garbage collector thread may want to collect the memory of these objects when the object is no longer referenced. And then it will invoke the finalize method in case this class contains a finalize method. So attacking Java deserialization vulnerabilities is all about finding classes that contains or can execute dangerous code from within any of these callbacks that can be reached by these deserialization callbacks, like read object, read resolve, and so on. And the basic idea is that the attacker will be able to control the data for any of the member values of these deserialized classes. So if those member fields are used in a dangerous way and can cause this remote code execution or writing files to the file system or things like that, attackers will be able to actually abuse that in order to achieve remote code execution. So apart from the well-known callbacks like read object and read resolve, you also have to look for callbacks like validate object, read object no data, or even the finalize method invoked by the garbage collector. So these boxes in red here are basically the places where there will be some code executed before we get the object back into our application code, so before we can even do anything to protect from the application code, right? And also, finalize will be invoked on this object where the attacker control the member fields.
Yeah, so just to give you a very quick and simple expression of how this can be exploited, this is a very simplistic toy example, so showcasing how this can be attacked. So just assume that this simple dangerous toy, which is a serializable class, is sitting somewhere on a target service, application service class path. And it's having a private field, a private string field, whatever it is. And it is also, interestingly, having an implementation of one of these magic methods from the red box of the previous slide that get executed automatically during the deserialization process. And in this example, the read object method is simply applying all the field values from the stream to read data from and apply that to the fields of this object. And this is obviously something that the attacker can control when serializing his payload before sending that. So attackers can set arbitrary field values there. And in this very simplistic example, this leads to a very dangerous code that is sitting in read object. In this very simple scenario, just runtime get runtime exec, and then when that gets deserialized, the command will be executed. And after that, there will be a class cast exception or something else happening because it's not of the expected type, what the application expects to deserialize. But this does not stop the attack since the code was executed before that exception was raised. But obviously, this was just a simple toy example. There's no such dangerous code having a runtime get runtime exec in any read object methods. But you can still get remote code execution using Java deserialization vulnerabilities. And just to showcase you one of the many exploit gadgets that have been used, and this is one very famous one from Chris Farrow and Gabriel Lawrence, released last year as part of the talk from them. And it's a chain of different sets of classes, so it's basically a gadget chain to carefully connect all the dots so that when something gets deserialized, the classes like annotation, invocation handler, etc. are triggered until an invoker transformer is used that finally executes something from runtime get runtime exec. So you don't need to read this in detail. It's just to showcase you that the real world exploitation scenarios are a little bit more complex than the toy example we just seen previously, but they still lead to full remote code execution.
So what if there are no methods that can contain dangerous code directly reached by any of these deserialization callbacks? Like, for example, the toy example that Christian showed us. So we can use proxies, right? So for those of you that are not familiar with JDK proxies, they are basically a wrapper around an interface. So when there is an invocation on any of the methods declared on the interface, this invocation will be intercepted and dispatched to the invocation handler. So every proxy needs to be initialized with an invocation handler. And the invocation handler will basically do developer stuff. I mean, what they need to do, maybe do some login stuff, some security controls, and then they may dispatch the execution back to the original method or cancel the invocation, or who knows. So this is very interesting for us from an attacker point of view, because attackers or the classes that are serializable can contain member fields that are of a given interface type. They are not defined as the implementation type, but the interface. So the attacker will be able to actually provide not the type that they were expecting, but a proxy implementing that type. And when any of the methods on this interface are invoked from the read object or any other magic methods, these will be dispatching the execution flow into the invocation handler invoke method. So as an image is worth 1,000 words, we have this toy example again. This is a simple serializable class that, as you can see, does nothing dangerous. It basically contains a comparator, and in the read object, it's comparing foo and bar, so nothing dangerous here, right? So the attacker can actually provide not a real comparator that is actually meant to compare things, but actually a proxy implementing the comparator interface so that when we call compare, we will be intercepting this method and dispatching it to the invocation handler. So now we can use this secure and safe gadget to actually dispatch the execution to a different part of the application that was not reachable from a deserialization callback in the first place. So let's say that we find a serializable invocation handler, like this example here, that contains, again, a very simple and probably stupid example that is executing a command in the invoke method. But we will see that there are similar invocation handlers out there. And now we will be able to dispatch or to connect the deserialization callback, and we'll move the execution flow into the invoke method of the invocation handler. So we found several gadgets that we reported in Python and Oracle libraries. One of them was in BeanShell. This BeanShell, how many of you are familiar with BeanShell? Probably no one, right? Okay. So BeanShell is basically a scripting library, like an very old version of Groovy that uses very similar syntax to Java, right? And it contains an invocation handler, that is this BSH XDis class, that basically intercepts a Java call and replaces it with a BeanShell call for a function with the same name and the same signature. So this is the code of the exploit. I don't know if it can be read from the last rows, but basically what we are doing here is we are defining a BeanShell payload. So this is basically Java syntax, right? We have our payload here that is basically popping up a calculator, and we are just defining this compare function that takes two arguments. Now we initialize a BeanShell interpreter, we load this function into the interpreter, and then we initialize this XDis class and extract the invocation handler using some reflection tricks. And then what we basically do is we create a new proxy, and this proxy will be implementing the comparator interface, and we'll be using our BeanShell invocation handler as the invocation handler of the proxy. So what we need now is a trigger gadget, something to move the execution from the deserialization callback into this invocation handler. And for that, you can use plenty of gadgets in the Java runtime. We use the priority queue one because it basically is initialized with a comparator, and at some point in the read object method, it will execute the compare function. So basically, we will send the priority queue to the vulnerable endpoint, that is deserializing untrusted data. It will be deserialized. The read object method will be invoked. The read object method will call compare on the comparator, but because we didn't provide a real comparator, but the proxy, it will basically replace the original compare function with our payload function and execute the payload. So we thought, probably as you showed, raising hands, that no one is using this library, right? No one knows about BeanShell, no one is using it. And we were surprised that many vendors like IBM, or JBoss, PRMS, PPM Suite, data virtualization, and many others like Apache Camel were actually affected by this problem. And our opinion about this is that developers are just putting loads of dependencies on their application, and some of them have transitive dependencies, and you don't even know which libraries your applications are using, and you may be loading BeanShell stuff on your class path that can be used by the attacker. So the gadget space for attackers is huge.
So regarding mitigation advices, so after the major news release that was making the rounds in the last months, there were some mitigation advices that were also being announced. And the first mitigation advice, and we're about to discuss a few of them, the first mitigation advice that appeared was just to remove the gadget class from the class path, rendering the target server no longer vulnerable because it's no longer having that very same class on the class path. Well, that's not really a good idea because it might break functionality. And there are tons of gadgets that have been found meanwhile and are still to be found. So that will definitely break compatibility. And also there are some golden gadgets, and you see some in a few minutes, which are gadgets that are simply sitting inside the JRE itself. So that's not relying on an external library, so that cannot directly be removed. So that's unfortunately removing the gadget from the gadget space is not really a good solution. What about the second mitigation advice that we observed? That's a more interesting one. This was an ad hoc security manager. So that's roughly speaking like a system-wide security manager, but only installed temporarily, just wrapping the deserialization code in your application and then uninstalled again. So in this kind of code example, you see something from the outside, something untrusted is getting deserialized here in these lines of code, And immediately before and after that, some security manager stuff is happening, which is effectively setting a custom security manager prior to deserialization and removing it or setting it to a prior state after that. So that tries to safeguard that very deserialization spot, which is a good idea in general, but and also these kinds of policies from these very short-use security managers can be quite strict, not allowing anything that attackers would like to do, like file access, socket access, or operating system calls or whatever. But it can be bypassed. We found bypasses for this technique by using a bypass gadget that executes at a later moment in time. So when having a deferred execution as an attacker, then that executes after the security manager was restored to the previous state, and there's no longer this very protection. And this can be done, for example, by using something that is relying on the finalize method to trigger off the gadget. And that is something that the garbage collector thread will call at a later moment in time. And we found several gadgets that can be used that way. So that's unfortunately also bypassable. A third mitigation advice that we observe, well, it's a more interesting one again, is a defensive deserialization approach, or sometimes called look-ahead object input stream usage. That's roughly speaking a custom subclass of the Java I/O object input stream, and it's overriding one method, which is the resolve class method. And if you remember from the sequence diagram at the beginning of this talk, this method gets called before the magic methods that fire off the malicious execution get called. So that's a good moment in time to hook this method, override it with a check. If the class name that we can see here that gets deserialized, then objects from this class get deserialized, is valid in terms of a black or white list. So that's an interesting approach, and you can then bail out if it's not valid according to your rules, using an exception or whatever, and then the attacker's code won't execute because it won't get deserialized. That's an interesting approach, and we've seen some vendors that were affected by the kind of Java deserialization vulnerability actually using this kind of approach. Mostly they used it with a blacklist by default, disallowing certain known gadget classes, and an optional whitelist that the developer, the user of the library or framework or whatever needs to fill, except one which did also use a whitelist by default. And some other big vendors also use only blacklists, and we cannot yet talk about that. That's still being fixed. But the outcome is, and you're on a security conference, so blacklists can always be bypassed. And we tried to find a way to do that, and we succeeded in doing that. And the idea is we need to find something that is causing a nested deserialization. So something like these lines of codes, being a serializable class, so being a gadget sitting on the server's target's class path, and in one of its magic methods, it's doing another deserialization. So deserializing something while it's deserializing something. Sounds a little bit weird, yeah? And in this example, we've got a byte array of whatever it is, your private field, that the attacker can control when serializing his payload. And upon read object, this byte array again, so when this class gets deserialized objects from this class, it's using a new unprotected object input stream to do a second deserialization, a nested deserialization. This is then not protected by the direct ad hoc usage on the agent-based ones of a look-ahead object input stream. Well, and we thought, is this real or just fantasy? And we did some research on that and let the numbers stand for themselves. Indeed, that's real. We found surprisingly many gadgets that can be used in this scenario as a blacklist bypassing gadget, even 2 within the JRE itself, many within libraries that are commonly used, and especially the class paths of major application servers contained lots of them, just due to having multiple or many jar files there. And we would just like to give you one example of these bypass gadgets. It's a very interesting one. It's sitting in Java X Media JAI. It's a serializable rendered image class as part of the Java Advanced Imaging API. And that's something that's very interesting because at the same time, it's a blacklist bypassing gadget and a ad hoc security manager bypassing gadget. So this class being available in the JRE is having a finalize method, and that method calls itself doing finalization from the garbage collector thread when the security manager was already uninstalled, the ad hoc protection, calls dispose, and the dispose method calls close client. And within close client, something strange is happening, so don't ask me why. It is connecting, upon finalization, connecting back to a server, depending on fields the attacker can control. So the attacker can set values of where to connect back. And as long as the target is able to do an outgoing network connection, then it will read from that very socket stream and deserialize using an unprotected object input stream from that. So that's a way to have a nested deserialization just in the simple code example from the previous slide. That's triggered off with finalize, so also bypassing ad hoc security manager protections. So obviously the idea would be to use some whitelist protection approach when using a look-ahead object input streams. But even when you're using these whitelist approaches, you might still be vulnerable to at least denial of service attacks, because there are some very handcrafted, very specially crafted attacks available that use carefully nested hash sets, hash tables, array lists, etc. in order to, when they get deserialized, either impose a very, very high memory load or a very, very high CPU load that effectively renders the application unreachable. So many whitelists have to include these very simple classes, otherwise they won't work with the business logic of the application. So using a whitelist approach at least might leave you vulnerable to denial of service attacks. So that's effectively ruling out the mitigation advice of defensive deserialization, at least with the blacklist approach as well.
So we've seen that we found, or people found, gadgets in popular libraries, like for example Apache Commons collections, or the one that we found in Bean Shell, some others in Spring libraries. But finding pure Java runtime gadgets like the holy grails, both for attackers and probably also for defenders, because we find gadgets in the Java runtime, we may get people to take this vulnerability seriously, not like in previous years. So we were searching for gadgets in the Java runtime so that the attackers don't require this dependency to be installed on or sitting in the class path. So for that, we actually took one of the gadgets that is publicly available and found by Chris Verhoeven. And actually, that gadget is only working up to Java version 7, update 20. So we tried to find another gadget working in Java 8. So we saw this post by Guter Quakerts, and basically he was talking about some tips and tricks around the annotation invocation handler class. And he found that the equals implementation class of this invocation handler was interesting because it's going to call all the zero argument methods on the argument on the object that is passed as the first argument. So that's basically what Chris Verhoeven used in order to get this Java 7 up to update 21 gadget. And he did something really awesome that is basically a chain of gadgets starting with a linked hash set that triggers this equals implementation method. So just as you have an idea of what Verhoeven did, he basically serialized this linked hash set. So the objects in the set are basically serialized. And when we read the stream from the stream, we basically take these objects and we push them into a hash map that backs up the linked hash set. So we will be calling hash map put with the first object in the set. That will be our payload object. The object that if we call a method on this object, the payload will execute. So we will put it, and when we call hash map put, hash map will actually call hash code in order to verify if there is another entry with the same key. So there are no other entries, calculates the hash code, so far so good. Then we will push a different object. In this case, it will be a proxy. As we said before, proxies are very useful for this kind of attacks. It's using the annotation invocation handler as the invocation handler of this proxy. And it contains a member field with this name, member values, with only one entry. The first one will be this string here, and then the very same payload object. So when we call hash code of the proxy, we will be basically intercepting the hash code call, dispatching it to the invocation handler, and the invocation handler will calculate the hash code of the proxy using this formula. So it will calculate the hash code of the key for every key. It will iterate this hash map, and for every key, it will calculate the hash code of the key and then sort it with the hash code of the payload object. This string here has a very interesting property. His hash code is 0. So we will actually make this first operand 0 and then sort it something with 0 that is basically the hash code of the payload object. So now we have a hash collision, and that's very interesting for us because when we have a hash collision, the equals method will be called in order to verify if the values of these keys are the same. So then we will call the proxy equals implementation that, if you remember, is the method that Guter found that it will be executing all the zero argument methods on the payload object. So with that, we can get our execution, the execution of our payload. So way before these gadgets were published, Oracle introduced a fix for something else that actually prevented this gadget from working on future versions of Java. And they basically deserialized the annotation invocation handler, so the object was completely deserialized, and then they were checking if the annotation invocation handler was actually wrapping a real annotation or not. And if not, they were throwing an exception. So back to this Wouter post, he was also proposing a technique to catch this kind of exception by injecting a fake field into the byte stream, and then use a gadget that basically contains a read object that reads another object within the read object, and then it catches the exception and basically ignores the exception. So with that, what we did was basically take Chris Verhoeven gadget, take Wouter's technique, and apply a lot of time, because it's actually very complex, and created this Java 8 up to update 20 because of another exception. Actually, this gadget can work up to even Java 9, but it depends on the payload type. So with the payload type that we are using, it works in Java runtime 8. So what about other languages? Is this just affecting Java? We saw all these media news in the first slides that Java is affected, that Java apocalypse and so on. Well, this is not true, because this is also affecting other languages on top of the JVM, like Scala, Groovy, because they basically use the object input stream from the Java libraries. So we don't have time to analyze these different approaches, but you have some test cases in this GitHub repo over there.
Yeah, so finally, what can we do then to mitigate this to a reasonable level? So as we dissected some of the announced mitigations, well, if you just take one sentence out of this presentation, please let it be the red one. Do not deserialize untrusted data. Just don't do it. That's effectively ruling out the problem for you completely. Better try to use some other remoting technology. At the long term, going to some JSON-based REST services or XML-based web services whatsoever. But bear in mind that for the XML-based stuff, even the same attack pattern applies of Java deserialization to Xstream and XML decoder-based solutions. When you're unmarshalling untrusted XML input using these libraries, you have to configure a whitelist, or otherwise you might be vulnerable to the very same thing as well, because they are using the Java deserialization callbacks under the hood without directly exposing that to the developer. And if you're not able to go away from Java deserialization just as a second best option, well then, not really much is left. Then you can use, or should use, the defensive deserialization approach, where you are using the look-ahead object input stream, but use it with a strict whitelist, because we showed you that backlists can be bypassed with the blacklist gadgets we found. Use a strict whitelist, and if you're not able to build this strict whitelist of classes that your application is expecting for deserialization, you can use, for example, just a very small Java instrumentation agent we released for this talk here. It's something you can use on a test system, obviously, only. And this test system then should be instrumented and will be logging all, when you're testing the application then, will be logging all the observed class names of classes that get deserialized in a distinct list for building up your whitelist for classic Java deserialization, as well as for Xstream-based ones, including stack traces where this is happening. So that's a nice approach to even find out where you're using, without knowing, deserialization within your applications. And if you're protecting your application with the second best option of using a lookahead object input stream, the agent-based approach is also interesting, because that can catch the backlist bypassing gadgets object input stream usages as well, but this might also create other problems. And you're still not protected against any of these DOS scenarios.
So how to find these vulnerabilities in code reviews? Basically, check your code for calls to object input stream, read object, and read and shared from object input stream that were initialized with untrusted data. So for example, this code over here that looks like another toy example is actually a real example from an application that we found unreported. So if you just passed untrusted data into an object input stream and read object, you are basically screwed. This is simple to find, but be aware that you may be using Java deserialization without knowing you are using it. So you may be using some library code, some framework code. You may be using JMS that is using some object message. You may be using JMX and passing objects to the RMI interfaces, or maybe using some Spring HTTP invokers that also use Java deserialization under the hood. So check which technologies, which frameworks you're using, and verify they're using Java deserialization under the hood. For that, it's very useful to use the SWAT agent, this agent that we created that basically will monitor the application running and will let you know if something is getting deserialized. So that was for finding vulnerable endpoints. What about if you want to find gadgets? You may want to find gadgets because you are an attacker and you want to, or a pen tester, and you want to verify that the application was exploitable, or because you are writing your own whitelist and you want to whitelist some classes and you want to make sure that those classes cannot be used for abusing your application. So in order for doing that, you have to look for dangerous code, like, I don't know, unsafe reflection calls, I/O operations that are writing files to the file system, maybe some nested object input streams that can be reached from any of the deserialization callbacks, like, for example, the read external, read object, or from the finalize method, or from any of the serializable invocation handlers. Because as we saw before, invocation handlers or proxies can be used to jump into different places of the code. So if you're doing that for, I don't know, you're going to whitelist 10 to 20 classes, you can do that manually, that's easy. If you are going to analyze thousands of classes, like we did, for example, if you are deploying your application on top of WebSphere, you will have more than 5,000 classes on your class path. So if you want to verify that none of them can be used for these attacks, you better use some kind of static analysis tools to automate this process. We actually use static analysis for finding the gadgets that we have reported. So,
yeah, and aside from the static part, what can we do during pen tests? So from the dynamic view, for pen testing applications and finding these vulnerabilities, you have to closely watch the traffic, the network traffic or web traffic that you're observing, and inspect whether they include any kind of Java serialization payloads. And that's quite easy to spot because Java serialization begins with some magic byte headers that you can watch out for. And also you should keep in mind that when it's exposing something to the outside via a web interface, for example, like a cookie and reading something back, or a hidden form field, we've seen these things happening. And then it's usually base 64 encoded. So for these scenarios, you need to watch out for different patterns, obviously, and also they could have been compressed prior to that, so that the magic bytes could be something else as well, just to watch in your network traffic or web traffic. And there are different tools that you can use, enterprise-wide scanning. You can even use very good tools like OWASP ZAP or burp for manual pen testing and semi-automated pen testing. And there are some plugins existing, like the Super Serial plugin for these tools, just to watch out for Java deserialization traffic in the web traffic that you're seeing. And there's also a serialized killer available, which is a script that performs a mass scanning of a network for vulnerable endpoints of major application servers and vendors' products. And aside from that, when you're using proxying non-web traffic, and then you might expect some PCAPs or whatever from Wireshark, you can use these tools as well, just in order to watch out for the magic bytes of where serialized data is floating within your network. And if you're allowed during the pen test to instrument the test system with an agent, you can use the aforementioned SWAT agent just to get logs with stack traces and class names that get deserialized in the application. So then you also see from the inner view of where in the application something gets deserialized. And just to close this presentation, so we want to leave you with 3 key takeaways. The first one is within the next week, you should try to find out where in your application landscape you are deserializing any untrusted data across a trust boundary, and try to find some, if it's a library or framework that you're using, try to find some patches or some updates that fix these issues, and apply strict whitelist configurations when they offer you to configure something like the Xstream thing does. And within the first 3 months, it really makes sense to think about moving away from Java deserialization to another remoting technology that Java supports, like web services or RESTful services or whatever, completely ruling out the tight coupling of Java serialization as part of the problem. And if that's not possible, then you should use a defensive deserialization approach with a strict whitelist, as we showed you, that blacklists can be easily bypassed using the blacklist gadgets. And obviously, within the 6-month time frame, it makes sense to include these kinds of checks from static code analysis and dynamic code analysis as part of your process. just also to ensure that the classes that are inside the whitelist that you configure in your environments do not contain any attacker-usable gadgets as well. So these are sometimes hard to find, and it makes sense to check even your whitelist classes that they do not impose a code execution risk to the outside world. So finally, thank you for attending our talk. We are still here for a few minutes for Q&A and throughout the conference as well. So we've got two links for you as well. It's a FAQ and a white paper, developer-oriented FAQ and a white paper about the topic, so that you can read up the things and details in a little bit more detail. And also, we've got our Twitter handles and email address, just in case you have any further questions. So thank you very much for attending the talk, and feel free to ask questions.
We have a good 5 minutes for Q&A. Thank you for a great talk, gentlemen. Any questions? Hang on. I'd like you to speak in the mic, please. No, it's Jim. Jim.
So, oh gosh, that was loud. Oh, right, okay. So you said if we only deserialize from trusted data, then that protects against this vulnerability. So what I'm wondering is, so I have, in an application that I'm working on, we have message signing between the front end and the microservices layers. But is there a theoretical vulnerability whereby somebody could come into my website and do something akin to a SQL injection attack, like a sort of deserialization injection attack, by putting something naughty into the fields that they know is going to be passed into that deserializer?
Yeah, very good question. So there are some second-order vectors that can be eventually used to facilitate these kinds of attacks, so that the attacker is injecting or placing his payload, poisoning some backend storage like a SQL database, when there are some columns that are used, and some vendors of SQL databases support that get deserialized, some Java object sitting in a column and gets deserialized when that's read. And there are even other stores, like other servers sitting in your application's landscape, that can be used to plant such data from an attacker's point of view, that then on the second stage gets deserialized. So as the data flows, so does the attack payload flow. So these kinds of data stores even then should be treated as untrusted data.
A brief note as you're heading out, there are red and green cards for you to evaluate the talk. Just put them in the bucket. But any more questions, please? Here we go.
More or less just following the same question, but like I haven't seen, but I was waiting for the juicy tidbits on somewhere out with the Hadoops and the Sparks, same kind of second order data exfiltration. Have you seen any research? Have you done any there, or just point in the right direction for that kind of stuff?
In terms of data exfiltration?
Exploiting data clusters.
So the question was whether we've seen something that is in terms of data exfiltration or exploitation. So the mic was not clear.
Attacking Hadoop with data serialization, I guess is what I'm saying.
Okay, so attacks during deserialization. Real-world attacks, yeah, we've seen something. We've seen real-world attacks, and we've seen something very interesting at the major companies from bug bounties as well. So this was just something that has been found prior to being exploited. And this was surprisingly a big vendor, a big company that was exposing this kind of data to the web layer. So there was something from a untrusted source coming from the outside of a hidden form field or cookies or whatever that gets deserialized back. So it gets sent to the client and then read back and can be poisoned as well. So this is something that we've seen. And we've also seen mass exploitations of servers, of application servers, in order to spread worms from these kinds of attacks. Unfortunately.
We still have plenty of time for more questions. I have a quick one. Are there any concerns with using the various defensive runtime agents on a production server?
Good question. So this might impose a risk due to licensing. I'm not pretty sure, but I haven't read all the details of the license agreement, but I'm pretty sure that on a production server instrumenting the Java IO object input stream could impose some trouble. And it also might impose some trouble in terms of scalability and eventually also threat model that might break. So the really only good solution that you can use is to do not deserialize any untrusted data.
So my question is, because I've been involved a little bit with the serialization stuff,
We recommend the JSON approach, right? We recommend the, go to Zaxby, go to JSON, right? But I always have this naggy feeling that, I'm recommending that going, but I have no evidence that they don't have the same problems. Like, apparently they don't, but like the Xstream and XML decoder, you could create the exact same thing in JSON. Have you guys looked at that? Because I haven't, and I haven't seen a lot of research on it.
Yeah, that's...
And I'm waiting for that sleeping giant to one go like, shit, this is in JSON.
Yeah, there are some interesting libraries that you can use for JSON opening or JSON parsing that eventually can get into interesting situations. We took a look at those, but not to that deep level, and I'm not expecting anything to come out of that leads to Java deserialization, code execution, but well, you never know. So even the Xstream thing was using the callback methods under the hood. So even for non-serializable classes, rendering the attack surface even bigger. So that's really a means of knowing what the frameworks and libraries you're using are doing under the hood, and then you need to protect this. And for this, an agent-based approach on a test system only is a good thing that you see what's going on from the inner view and not only from using the API.
Any other questions?
Hi. So my question is about the Java object signing. So will the signature help in protecting from this attack? So the root causes.
Yeah, so code signing in general is a very good idea, but it depends on when you're a hoster. Then you can run code that has been signed, and then you can impose certain trust levels on this, or you can run code on the client. But this is something different then. There are even things like signed object and sealed object that you can use in Java to seal or sign the state, but it's not really protecting completely against these kinds of attacks.
Any other questions? No more questions? A big round of applause for Christian and Alvaro. Thank you for a great talk, folks.